Okay, uh, so I just wanted to show you something that I built in the recent days. And yeah, the file is named autodiff.ipynb, as in like automatic differentiation. But all in all, what I basically built is a neural network. Yeah. So let's just start. You got the main code, which we'll not go into right now, but yeah, it's pretty big. I know it looks small because I've like folded it all, but actually it's pretty big. Yeah, and there's a reason why it's so big, because I want to kind of show the process behind it, not just make a very useful implementation. So first, let's just start from like the basics. What is automatic differentiation? Well, automatic differentiation is something where every variable receives its gradient from the dependent variables on it, right? And so doing this in the reverse topological order, I shouldn't be using heavy words, but doing this in the last to first node, as in the latest to the oldest, you can send back all of these gradients to the nodes, and then eventually you'll reach the edge cases, that is, the nodes which do not have any variables that it depend on. In those cases, and I'm saying nodes, by nodes I mean variables all of the time. The variables could be a matrix, it could be a vector, it could be a scalar, anything that you can think of. So there are like three things: variables, functions, and constants. And functions is also just another like way of saying variables, but I've implemented it differently in the code, so never mind that. But yeah, all you basically have to do is just let's just actually kind of see something. So for example, look at this graph. I'm just gonna not copy it, I actually want to like open it. Whatever. So this graph over here, this is the output node, as in this is the value that we want, but it's depending on this other green node, the star node, but that's depending on this star node, but that's depending on x, which is a variable which I have colored in red, and on a constant 2, which we don't really care about, because constants are not updated during gradient descent, so we don't really care about that. We only care about the variables. In fact, we don't also care about the functions while updating stuff, because the function values we can just calculate once we have the variable values. So yeah, just like you get the gradient, and when I say the gradient, I mean the optimum value in which your node should move, or the value of your node should move, so that the final function is descending. So in this case, the final function is the final function is ascending at the steepest ascent rate. So in this particular case, for this last green node, it's the final function itself. So its gradient is 1, by which I mean either the identity matrix or just 1 itself, the scalar. In any case, this goes back, right? So now that you have 1, you can figure out what's the gradient of this thing using multivariable chain rule, and the gradient of this will be given by the chain rule. Once you know that, you can figure out the gradient of this guy. When I say gradient of this guy, I mean actually like the gradient of final function with respect to this guy, but yeah, just shorthand notation for that. I should really just say gradient for this guy, right? So the gradient for this guy, then you finally get the gradient for x. And once you do all of this, all you have to do now is just descend x along the value of the gradient that you got for x, and hope that your final function output will be descending as well. Right, so let's just run this. So this particular is you got some curve which I have defined like this. You got some curve like this. So x is a variable in red, and y is some complicated function of x. Yeah, it's like sine of x squared times 0.01 something. And what we want to do is find the minimum value for y. So we set a dt value, which is kind of like the step size, how much do you want to update x, and then we descend for 1000 such steps, and finally we get like what's the minimum x value, x value for minimum and y value for minimum, which is basically the minimum y value, and we just print out those things or plot those things or whatever. and this is what the output looks like. You got this curve and then you got this red thing. So let me just run this real quick. So yeah, it like runs in real time. 1.2 seconds is all it takes, and so the loss function, which is basically what this last function is, that went from 0.009 something to now 0.00018 something. So that's like progress, and so it came at this point, right? But that's just one very silly example, because this is not what we are going to do this. Like, I'm not building all of this just for these simple tasks. Let's go to some slightly complicated tasks. Okay, first let's take baby steps. Our first task will be, well, we want to rotate a unit vector to match another unit vector using automatic differentiation. And so this is the graph for the same. It's slightly more complicated than this simpler one, but yeah, all in all, it's still a simple thing. So when I run this in 0.3 seconds, it like gives us the loss function being -1, which is to say that it gives and over here notice that I've written a equal to minus dot something. What that means is, like, since I want to match the unit vector to some other unit vector, their dot product would be maximum when they are matched. So I want that condition for my lowest point thing. So what I really have to minimize is the negative of that, and that's why negative dot. But in any case, it doesn't really matter. I mean, it does this. Yeah, I mean, if you can get like used to the weird notation and stuff, it's okay. Yeah, so that's another simple example. Let's go to a slightly complicated example. First, let's just train the neural net on self-made data. So the final kind of implementation that I made for neural networks, that's using layers, which are matrices, and sigmoid functions and all of that stuff, and bias and that. You know it, right? 3Blue1 Run has a good video on it. Watch it if you want. So it's like, it's gonna take 2.3 seconds, it seems. Okay. Well, that's not 2.3. Okay, 4.7, whatever. Oh, so it actually went to 100%. That's weird. It's just a lucky hit that it went to 100%. You saw that previously it was 90 something percent. And just to show you that I'm not cheating or anything, I'm gonna run it twice or thrice. So now it's 89%, which is like pathetic, but well, whatever. All it means is that it's not converging, as in I'm not running it for enough time and with small enough steps. But I'm not gonna do that. I'm really just not gonna do that because it takes time, and when you are running this just to test it out, it's probably not a good idea to do it like full in depth. So that's just training this on self-made data. What about a real problem? So there's this data set called breast cancer data set, and sklearn provides it. And by the way, I did not use sklearn for this implementation at all. I'm only using it to get the data. So we just like use that data directly, right? And this is actually the more complicated neural net, which is like better, but let's go to something simpler. Let's go to just a neural net implemented with, perceptrons. So perceptrons is like, these are the fundamental kind of entities that you have in any neural net. Like, these are analogous to neurons. And so for this particular neural net, I have a layer of 5 perceptrons, and then these perceptrons feed into another perceptron, and then I take the loss function, which is just the mean square error. Although I'm not taking the mean at all, it's just a squared error, sum, so all of these nodes, well, these are like the column vectors of our data set X, capital X, right? Just separated, and then Y is, this Y, just that column vector, and just put in a node, right? So let me just run this. Let's hope it does this quickly. I have a bad feeling that it's not going to be quick. So sometimes you have to wait for like 30 seconds or so. Happens. Just, Alright, it's taking a lot time. Okay, 23 seconds. That's bad because last time it was 20 seconds. Why do I feel something's wrong? What if it's... oh god. This should not be happening. Why is this 35? Okay, we'll just be patient and let's wait. Ideally it should have been done in like 20 seconds or so. Okay, this is a bit too much. Okay, fine, that was bizarre. It shouldn't be taking this long. I don't know why this happened. But yeah, so you got your output. Before your loss function was 187 something, after the descent it's now 33 point something. And your accuracy, because by the way the breast cancer dataset is a binary dataset, so I can just get the accuracy by doing like whatever predicted value I have, just compare that with the actual values and then just take a mean of that equality stuff. Take this as like boolean values, 1 for true, 0 for false, and yeah, you get this mean which I convert to percentage, and that's like accuracy. So this is 94.9% accurate, but that's not on the test data. That's only on the training data. That is, you feed anything from the training data, it will give you with 94.9% accuracy what the output value, what y should be. But that's not enough. We want to do this for untested or data that we didn't train our model on, right? So let's actually also go to a more complicated and advanced model with like matrices and do that as well, right? Let's test it out on a test data. So over here, once again the same data set, and I've split it into training and testing data, and now I train this neural net for my training data, and then I predict what's going to happen from my test data. So let's run this, and like meanwhile while it's running, I'm going to tell you a little bit about why did I start with automatic differentiation. I mean, honestly, I just initially thought I need something that is more general than just neural net, and everyone else is just like doing, from my campus at least, is doing neural net like directly just implementing it without really caring about its general like structure. So I thought I should do that. I should like actually care about the general structure, the general minimization problems, and actually like basically build something like TensorFlow. And so I built this automatic differentiation technique library, I don't know what to call it, and then eventually it turned out that, oh well, apparently building a neural net isn't that hard. The linear algebra isn't so complicated as it seemed once you have automatic differentiation at hand, and like very light syntax to test out very complicated stuff. It's not that hard. So really, this was like one of those points where you had to do it, otherwise you would have lots of trouble building something good. So automatic differentiation that like really saved a lot of time, and that's why the file is still named that, and it's uploaded on GitHub with the same name, although it's not at all about automatic differentiation at this point. But yeah, by the way, our results are here. So we trained the data, and now it's like 97.67% accuracy on the training set, and on the testing set as well it's 97.77% accuracy. And by the way, the testing set is completely independent of the training set. As you can see, like I just separated it, right? And no, x test, y test is not a global variable. It's not like I'm cheating behind the scenes. I mean, of course you don't need to, you won't doubt me, of course, but just if someone does, well, I'm not cheating, okay? This actually is correct. Like, this is in fact the accuracy that I got after all of this, and you saw it, like I read it live. I'm even validating myself. Anyway, so look at this complicated graph. Right, there's a lot going on over here. So you got x and b, which are, why is this called b? It should be called mu or something, whatever. Now these are constants as well, but that's probably not good. But this is like after you normalize. So this part, like the first two green nodes, those were just so that you normalize the data. as in subtract the mean of the data from it and then divide by the standard deviation, which is done by this W matrix, which is basically just the inverse of the standard deviation converted into a diagonal matrix. And then this second green node that contains the value of our normalized data, it's written over there. And then actually the real stuff starts. So layer 1, which is this part, it has two variables, W and B. So B is a bias, which is like a vector that you add to your big matrix X. And when I say add, I don't mean like add along the rows, I mean add along the, how do I even say this? I mean you'll know about it when you actually read some stuff about it. But yeah, basically B and X have the same number of columns, sort of. B is not actually a matrix, it's just a vector, but well, yeah, the columns in X, that number is the same as number of elements in B. That's better. Okay, and then you subtract B from this X by broadcasting and all of that. NumPy does it automatically. And W is a matrix, which is so let's just say number of rows of W is the number of columns in X, but the number of columns in W is the number of what was I going to say? Number of rows in W is number of columns in W. What's that, by the way? Oh yeah, okay, that's the number of columns in the next layer, as in the number of perceptrons in layer 1, if you will, right? Yeah, I know, complicated. So this is like just one layer, and that's what I did. I just like trained it with 5 perceptrons in a single layer, and implemented using matrices. And this is like finally, you get layer 1. You just okay, why is this W over there? That's kind of weird though. That's why predict. Oh yeah, okay, that's another layer, sorry. So that's another layer without the B thing. And yprod is actually, ypred, that's like the output of a sigmoid function, and layer 1 was actually also an output of a sigmoid function. And unfortunately I didn't write them as sigma functions and just named them as the name of the layer. But yeah, this green node, it's supposed to be a sigmoid function, and its output at the rate just means like matrix multiplication. So I got the input from layer 1, so the output from layer 1, and took it as input, multiplied it by the weight for the layer 2, and it's not layer 2, by the way, it's like going from the middle layer to, well, okay, yeah, it's second layer, fine, sort of. If your X is layer 0 and middle layer is layer 1, then Y would be layer 2, you could say it like that. But the number of middle layers is 1 in this neural network. Right. So what was I saying? Right. I took all of these perceptron outputs, then I used them to create another layer of perceptrons, and these perceptrons I clumped together to think, well, okay, this is our predictive value for Y. And so since we only want binary data, we will just take one perceptron, which is what I did in the last example that I showed you, with the thing pretty explicit using perceptrons directly. And so once we got the Y predicted, we just get the loss function by doing all of this stuff. So yeah, right. And then why is this thing over here? You might say, well, that's like just my bad because the coding is slightly weird. So that's why I just do a loss function plus 0 all the time. But well, never mind. That's just something bizarre that happened. Well, anyway, this is the graph that we use to like minimize the final output, which is the loss function itself. And we do that by altering these 3 variables, the first W, this B thing, and then another W. So W are matrices, B are vectors, X was a matrix, convert that to a normalized data set matrix, right? And then finally you get like the output after doing all of this process. So when I say predict on X test, Y test, all it does is that it changes X with X test, the matrices, not the nodes. The nodes are wherever they are. and it changes y, this black thing, with y test, and then it runs the same process, like it goes forward. It doesn't descend, by the way. It doesn't train on that at all. It just descends. Sorry, not descend. It just propagates forward, right, once, and that gives you the loss function. It gives you the predicted value and all of that. And so, like, I don't know, I can even run it like separately, just so you know that I'm not training the model on that. See, 0.3 seconds compared to 27.1 seconds. And the thing is that this is like a 500 something row matrix, capital X. So I've only like took the first 300 entries for the training, and then the remaining everything, which is by the way 200 or something entries, those are for testing. So both of these have comparable sizes, right? So one running in 27.1 second and one running in 0.3 seconds means something is different, right? The thing is, we are predicting over here, we are not training again. So yeah, it's like working like perfectly. So now I guess we can finally get into the implementation and the math and everything. So this we did, this we also did. So usage part is done. Let's go to the main code. Oof, it's gonna be a long ride. So the libraries, and I'm using this GraphViz library to like create these graphs, which are completely irrelevant to the actual neural network. I'm just doing them because I want to explain what's going on. Then I have these global variables, node collection variables, and counter. I know people hate global variables, but like whatever, just have to do it. And I have the basic class for node, which like stores values. That's about it. It's just a container like for some value, and it has these functions which are somewhat important. So the most important function is receive. Receive basically gets the gradient from output nodes. It like initializes its own gradient to be 0, and then it like gets everything from the output nodes, and that's how you compute the gradient for any kind of node. Yeah. So by the way, the matrix nodes that I don't know how, yeah, we'll have to call it that. The matrix nodes that you have, those do not have this receive function active, as in I've set those receive function to just do nothing functions, and there's like good reason for that, because I was it was a complicated issue, but let's not talk about it. Okay, then you got this function node, which is like, okay, it gets 2 or more inputs, usually 2 inputs, and then it outputs something, but it also can get the gradient once its own gradient, or once the gradient for it, right, is computed. It can send the gradients for the input nodes to the input nodes as well. And I shouldn't say send, I should just say it just computes and stores it usually, but for a special kind of function we send it, and that special kind of function is called a mat function, which is for matrices, because I somehow implemented it differently. Like the mat function that's actually doing it the way it's supposed to be done. It's like back propagating from the back, right? So it has a send function rather than a receive function. Then there's a constant variable which has this receive function being do nothing, and the forward function also being do nothing. The forward, by the way, is a function that we run whenever we want to compute the value for the node. Then I have this function toNode, which like converts any normal value, like the number 1, the integer 1, float 0, something like that, to a node, which is pretty handy because you do deal with integers and floats and lots of other stuff, numpy values. Okay, then these functions are like the standard functions that any kind of library would have: addition, multiplication, exponentiation. Oh, okay, by the way, this exponentiation, that's like e power something. This power is like x power something. Right. Negation, just negative of x. Dot. So that's not like standard, by the way. But yeah, it takes the dot product of two vectors, or a matrix and a vector, just as NumPy does. But yeah, then sum, it like sums up all the entries in a vector. I also have this sum m something. Okay, I haven't created it. Okay, then I have the sine and cosine functions as well. I didn't use them, but I made them because I just thought, okay, for completeness I'm gonna do that as well. And this is only for vectors for now. Then finally go to the matrix functions. So multiplication, of course, matrix multiplication. Then the dot m. Dot m is a special thing. It's the inner product of two matrices. You also have this add m function, which adds two matrices, but it also adds one matrix to a vector. And that broadcasting stuff is like taken care of. You have neg m, which negates a matrix, pretty easy. You have square norm m, which is a new thing. It's not in normal libraries, but it basically, computes the, it's called a Frobenius something, that norm of a matrix. Okay, and then I have these non-class functions, which are like actual functions. So first the sign function, which just gives the sigmoid as a node, of course. Then you got this layer, which gives a whole layer, a bunch of perceptrons, or I guess, yeah, in this case it's not a bunch of perceptrons, it's a matrix basically. So that's what a layer thing does. Then you got squarm, which is the square error for a matrix, which basically takes in two matrices and then just give the distance between these matrices, the Euclidean distance, right? It's sort of weird, but yeah, that's what it does. Then you got a perceptron, which is it just creates a perceptron. Then there's this square thing, which is like a square error for vectors. Then you got backprop and forprop, which are one of the most important things in this whole collection of functions. So backprop is like backward propagation, it just propagates once. And forprop is forward propagation, it propagates once as well. And then this thing, backtracking descent, well, it's not working. Yeah, I'm gonna say it blatantly, it's not working yet, but let's hope it will work someday. But it's supposed to be backtracking linear search and then gradient descent, and it was working fine when I initially started dealing with all of this, and I even used it in a project of mine, but for some reason, I don't know, this is not working right now, or more like it's working really bad. That's the better way. It's not giving me errors or anything, but it's just bizarre, it's bad, that's what I say. And finally you have this descent. Descent is the gradient descent, vanilla gradient descent, nothing extra added, no backtrack linear search, anything, just descent. And yeah, that's pretty much it. Then you got this reset function, which resets the graph and other stuff. It clears the whole graph. And you got show, which shows the graph as you can see with eyes, that kind of thing. But yeah, and then you got a sigmoid. I don't know why it's here instead of up there, but it computes the sigmoid of a vector. Oh, I also have this function, capital SIGMM, which is the sigmoid of a matrix. And then finally you have the culmination of all of this, the final two classes, the perceptron net, which I'm not going to use ever again because I have a better thing, which is the layer net. Layer net is pretty complicated. Yeah, just truthfully it's complicated, but it's basically the whole neural net, every single thing combined together to create one neural net. And it has a few options as well. You can either normalize your input matrix, and you don't have to do PC after that because you just normalized it, and then that's pretty nice. And it also helps because when you divide by standard deviation of the vectors of the columns, what it does is that it removes that problem of the exponential exploding. Okay, what do I say? The x function evaluated on the matrix exploding. It removes that problem because now you don't have very large values. So the sigmoid function works correctly basically if you do this, if you do normalize. If your values are just I don't know, 0 1 0 and something like that, then you don't have to do all of that stuff, right? And then you also have this middle thing, which is basically like the number of perceptrons in each layer, or each middle layer I should say. So that's layer net. And yeah, that's pretty much it. I don't get it though. Why do people say it's like some complicated, bizarre technology when it's really doable? Of course, it takes lots of effort, but it is in fact doable. And given enough effort, anyone can do anything. That's what I believe. And that's what I did. So I now have a neural network library, I shouldn't say, but implementation of a neural network. Yeah, sort of. I wonder if this compares to something like TensorFlow. It probably doesn't. It probably doesn't. But well, anyway. Oh, and this is like unnecessary import. This I guess is used in PCA when I was doing the thing with perceptrons. So by the way, the perceptron neural net thing that I initially built, which was in fact what my initial idea was, that I'm just going to do this with perceptrons directly. Let's not even go to matrices. This is very slow, right? And the reason it's very slow is because Python is slow. But when you do this with NumPy, it's fast because NumPy is in C. And so that's why I had to go to matrices and not just rely on perceptrons. And so to actually like even use the perceptron neural net for anything, I would have to, reduce the size of our data to a lot smaller something. So for example, breast cancer, this data set has 30 columns, but I did PCA and then reduced it to just 7 columns, and that's why I had this EIG function somewhere, yeah, right, imported from NumPy, because it gives the eigenvalues. Yeah, right. So PC is like pretty old at this point. You of course understand all of this, I think, I don't know, but yeah, that's it. So I'll see you guys in the next video. Bye.